Okay, now we have all the prerequisites that we need to optimize actually LDPC codes on general channels. And this is what we're going to do now. So we're going to use the exit chart, and we're going to use the same kind of approach as we did before. But let's take a closer look at what we are going to do exactly. So first of all, we start from the exit chart, and we essentially start from this condition. This is the condition that we would like to fulfill. And this is the condition that the code converges. There's an open tunnel in the exit chart, and we can iterate between variable node and checker nodes. So this function depends on the continuous IAV, and IAV is between 0 and 1. 0 is included and 1 is not included, because the two curves, they will match exactly at 1. They will always be at 1, so we don't include point 1. Otherwise, we cannot have this strict inequality kind. But IAV is continuous, so again, we do the same thing as in the binary erasure channel. We discretize IAV. So that's what we do. So we discretize IA, both IAV and IAC, we just call it IA, in the interval 0, 1 excluded, into, again, capital D steps. So we set IA tilde to be I divided by D, and I going from 0 to D minus 1. So we transform this continuous exit chart problem of the two curves not intersecting into a discrete problem. And essentially, the optimization problem is very similar to the B-C case. We would like to find the largest possible rate for a given signal to noise ratio, given mu c. The only difference is that the exit chart approach doesn't work for irregular check node degrees. So the check node must be regular. So we cannot use DC average, but we fix a regular check node degree DC. Makes the problem a little bit simpler, but it reduces the search space a little bit, so the codes may not be perfect. But still, we will have very good, see that we get very good codes. And then, of course, we need to take into account the stability condition. So here is the optimization problem. Our target function is the maximization of the sum of lambda I divided by I. And if you recall from the binary erasure channel case, this is equivalent to maximizing the rate RD. We fix the check node degree, so we fix DC. Then maximizing the rate is equivalent to maximizing this term. And then, of course, we need to have the usual conditions. Lambda i's must be larger or equal than 0. Actually, they must be between 0 and 1. But they also need to sum up to 1. So if they are larger than 0, and we require them to sum up to 1, they must be necessarily between 0 and 1. And then we have the things that change. So this is the convergence condition. Doesn't fit into one line. We put it in 2 lines. This is the convergence from exit chart. And this is just the same condition that we had before. So sum over lambda I, so it's linear in lambda, times this guy. This is just a constant. This is something that we can pre-compute. Must be larger or equal than this guy, which is also something that we can pre-compute. And this must be true for every j between 0 and d minus 1. And then we have the stability condition. That's the last one. This is the stability condition. So here we plug it in for the binary input AWGen channel. So lambda 2 must be smaller or equal than e to the power mu divided by 4 divided by dc minus 1. And we can solve this problem using numerical tools. And to illustrate, we'll just show how this is working or how this works by taking our usual numerical optimization. So we have our Jupyter notebook here. And the first thing we need to do is we need to implement the J function. This is what you can see up here. So we have the J function with those constants. So we can just implement our J function. This is actually very simple to do. So, and we can also invert the J function, which is also very simple to do. And then we have our optimization problem. So for a given E as of n0, for a given check node degree, and for a given maximum variable node degree, dv max, we find the code of the best possible rate. We do this by solving this optimization problem. So implementing this optimization problem is simple. So we have our function find best lambda. So we give mu c, dv max, and the check node degree dc. We use 500 discretization steps. So we go between 0 and d, and discretize this in d, between 0 and 1, discretize in d steps. And then we define our variable. So we would like to optimize a vector of length dv max, which is a variable of our convex optimization toolbox. We use cvx_pi in this case. Then our objective function is we maximize the sum over lambda I divided by I. This is the equivalent. So we write this, the sum over lambda I divided by I. This is equivalent to say that we have a vector lambda transpose times a vector c, and the vector c is equal to 1, 1 over 2, 1 over 3, 1 over 4, and so on. This is an equivalent way of expressing this summation. Note that here we start with 1. Here the sum starts with 2. We fix this by setting lambda 0 or lambda 1 equals to 0. Because we don't want to have variable nodes of degree 1, as you're going to see in the tutorial session as well. So this is what we here. So this is the objective function. We maximize lambda vector lambda transposed times CV, and CV is just 1 over 1, 1 over 2, 1 over 3 in a vector. And this add operator in Python means vector-vector multiplication, vector matrix multiplication. Then we have the constraints. First constraint, the sum over all lambda I must be equal to 1, and all lambda i's must be larger or equal than 0. Then we don't want to have variable node of degree 1. This is lambda 1 must be equal to 0. And for implementation reasons, because it was slightly easier this way, we flip the lambdas. So the first entry in this vector lambda is lambda dv max. The next one is lambda dv max minus 1, and so on. So this is why just differently arranged, but this means that lambda 1 should be equal to 0. Then we have the exit chart tunnel. So here essentially we go over the range of different discretization steps. For each discretization step, we add a constraint, which means that lambda times sum over lambda I times the J function should be larger or equal than the right-hand side, which is given here. And we just put one side and say they must be larger or equal to 0. We don't have strict inequality because convex optimization toolbox doesn't care about strict inequality. It will converge to equality. So it cannot handle, numerically, we cannot handle strict inequality, because it would be the same number plus some small delta, some small epsilon, which is essentially not representable. Then we have the stability condition. That one is given here, and then we just solve our optimization problem. We have this, then we can make a try. So for instance, for a channel with a mu-c of 3.8, what is the second? The second is maximum variable node degree 16, a check node degree of 14. We can calculate the best possible polynomial, and that's what it gives us. If we change the check node degree, for instance, 11, then we get a different best polynomial. So we can 14, we can increase the maximum variable node degree, for instance, to 50, and doesn't really make a difference if we use a higher variable node degree because it's not necessary to be used here. Okay, so this is how we can find. We can play around with this a little bit. Here we have a small widget. So we have the exit chart and the channel mean parameter. So you can play around with channel mean parameter as well. And then you can take a look at the resulting exit chart and the resulting polynomial. So we crank up dv max to 18. And if we increase the mu, you will see that the variable node curve will go up. So the initial point will move up because you will have a better channel. You will start with a higher mutual information from the beginning. If you decrease mu, you will have a lower initial mutual information and it becomes more challenging. If we increase the check node degree, then the check node curve will move up and the code will become again more challenging. But if we increase the channel quality, we'll have some space again. Here we can crank up a little bit again. And you also see if we crank up the check node degree, the rate will also increase. This is the byproduct. Increase the DC, you'll see an increased rate because the rate is in the numerator. So it's 1 minus DC over sum of lambda IDI. So if we actually increase DC, we also increase the design rate. So actually, it's 1 over DC that's inside here. Okay, so we have that one. So we can play around with this a little bit and get a feeling for the different parameters, how the exit curves change and how everything changes in here. Okay, so now how do we do this for the optimization of the code itself? So again, we use an example and we look at the very same example as we had before. So we'd like to optimize the code of target rate 0.7. We fix DC max or dv max, and then we sweep through DC. We can fix a threshold T delta, and then we just use a binary search. So we start with a given mu-c, start with a given delta mu, and then we sweep through the different DCs, select the one that leads to the largest rate. You can see the rate expression. So you see that if we increase DC, this term, because of the exponent -1, will decrease. Then we have a minus sign, so the rate will increase. So this is the leads to the largest rate. And if that one is larger than the target rate, means our channel is too good. We need to worsen our channel. We do this by reducing the mean. And if our rate is smaller than the target rate, it means our channel is too bad. We need to improve the channel, and then we need to increase mu-c. And then we just repeat this until we narrow in or home in into the finally desired rate. So again, we can take a look at an example. Here's an example. We start with mu-c equals 10. We sweep DC between 0 and 22. So we have a target rate that is kind of large, significantly larger than the target rate is our RD max. So our channel is too good. We need to worsen our channel. So our new mu-c becomes mu-c minus delta mu divided by 2, which is in this case 5. So I repeat the same thing. 5. And here you can see the discrete points of our optimization. And you will find that now we get a RD max of 0.789. Again, larger than our target rate. So again, what we do is mu c becomes mu c minus delta mu divided by 2. So this becomes 2.5. So we repeat the same, so wrong direction, same thing for 2.5. Now we find a rate that is smaller than our target rate. So our channel was too bad. So we need to improve our channel. So mu c now becomes mu c plus delta mu divided by 2, which would be 3.75. And with 3.75, we are again below the target rate. So again, we need to increase mu c a little bit. Then we are again above. And by this, we are targeting in on 0.7. And after 10 iterations, we found a code of rate 0.7 and with parameters mu for threshold of mu c equals 3.8086. Here's the degree distribution of this code. So it has a regular check node degree of degree, not 13, but of degree 14, because this is always the degree minus 1. And this is the variable node degree distribution. The variable nodes of degree 2, of degree 3, of degree 6, degree 7, and of degree 16. And the threshold is minus 0.13 dB in ES over N0. And this is roughly 0.6 dB away from the capacity of the channel. So it's a pretty good code. So we can see the exit chart of the optimized code here, and you see that it's also well matching. So let's take a look at our code again, and let's take a look at an example of how we can do the optimization ourselves. So let's pick some parameters, for instance. So here's the code to do the optimization, and we can, this is for one specific step that you can, so you can do it by yourself. Either you can sweep it for yourself interactively, or we can try to do it. Here you can change the maximum parameters and the mu c, and then run the optimization and see what you get. So this is the best code for, we have for this particular channel, you have a code of rate 0.478, average check node degree of 7, and a corresponding polynomial. So now, for instance, we can start looking for code. So let's say we want to have code of rate 2 over 9. Say our DC max is equal to 10, and our DV max is equal to, let's put a quite big number, 40 here. So, and then let's try to do the optimization. That should be pretty fast. So we start with an ES over N0 corresponding to 4 dB. This is a mu c of 10. Here we find the best possible code, but it's of rate 0.8. So we need to run the optimization for a worse channel. So we worsen the channel, go to mu c equals 5. Still the rate is 0.74. So we need to decrease again. And ES over 0 minus 2. We find a code of rate 0.56. So we need to decrease again. And code of rate 0.35. So we're getting to a good direction already. And let's see, let's let this run for a little bit further. So we have a design rate that is now 0.2. So we're pretty close to 0.22, which is 2 over 9, so 0.22 bar. And it was okay, overshoot a little bit, so we need to worsen the channel again. 0.22 for 4. And 0.225. reasonably close. 213. It takes some steps until we getting there. But we are approaching the final code. And this is the final code that we have. It has a slightly lower rate, so it's not well suited. So you may want to try with a different starting point of M.Sc, because the M.Sc I started from was just somewhere in the middle. Was not targeting low rate codes. If you really want to go for low rate, you may want to start with a smaller M.Sc as a starting point. This is the code you get. So actually here you use quite a lot of degree 40 variable nodes. So 25% of the edges are connected to degree 40 variable nodes, and this is the remaining degree distribution. This is of course lambda. So in order to construct the code and the tenor graph, you would need to construct the polynomial L of Z, which gives the degree distribution from a node perspective, which is better suited for definition of the design of the parity-check matrix or the tenor graph. Okay, so let me come back to this. So so we'll stop here, and then we'll have the binary symmetric channel as a separate video.